The universe is not a frozen monument. It is a vast ocean of blackness, stitched with light, stretching endlessly in every direction. Yet this ocean does not rest. It swells, it spreads, it tears itself wider with every passing moment. There is no sound to mark its movement, no ripple that the ear can catch. The expansion is silent, yet it is the loudest truth of existence, a constant widening that carries galaxies away from one another, like ships drifting apart on a tide that never turns. For centuries, the human mind assumed that gravity would rule the cosmos, pulling all things back toward each other, binding stars and galaxies in an eternal embrace. Even Einstein himself imagined the universe as steady, unchanging, balanced on the knife's edge of gravity. But the universe betrayed this expectation. Instead of slowing, its growth quickened. Instead of collapsing, it rushed outward. An unseen force, invisible and immeasurable, began to push space apart. Physicists gave it a name, dark energy. But the name explains nothing. It is neither dark nor known to be energy as science defines it. It has no direct detection, no laboratory experiment that confirms its nature. It is a paradox written across the night sky, a silent expansion that no law of physics can fully contain. It is the universe itself, whispering a truth more unsettling than collapse, that reality is driven by something unknown, something beyond the reach of every equation. And so begins the mystery that defines the fate of all things. Chapter 1: Discovery Phase. The early 20th century was a time when the universe seemed eternal, still, and unchanging. Astronomers peered into the night sky with the largest telescopes humanity had ever built, convinced that the cosmos was a quiet stage Scalatese frozen in position, its stars timeless, but hidden in faint smudges of light drifting across photographic plates. A revolution was waiting to be unveiled. At Mount Wilson Observatory, perched high above the lights of Los Angeles, Edwin Hubble began to measure what no one had dared to question: the distance to the spiral nebulae. With the powerful 100-inch Hooker telescope, he examined Cepheid variable stars, cosmic lighthouses whose rhythmic pulsations revealed their true brightness. By comparing their intrinsic brilliance to what reached Earth, Hubble calculated distances with unprecedented accuracy. The results were staggering. Many of these nebulae were not clouds within the Milky Way, as many had believed. They were separate galaxies, each containing billions of stars, scattered across a universe far larger than anyone had imagined. The cosmos had suddenly grown from a familiar island to an endless ocean with countless shores beyond the reach of human sight. But it was not just the scale of the universe that shattered expectations, it was its motion. By studying the spectra of galaxies, Hubble noticed their light was shifted toward the red end of the spectrum. The greater the distance, the stronger the shift. This was not a random trend. It was a law written into the cosmos itself. The galaxies were receding. Space was stretching. The universe was expanding. This single realization overturned centuries of thought. For generations, philosophers and scientists had assumed the cosmos was static, perhaps infinite, but stable. Albert Einstein himself, in 1917, had constructed his equations of general relativity under the same assumption. When his mathematics suggested that the universe must either expand or contract, He introduced the cosmological constant to force balance, a mathematical fix designed to freeze the cosmos in place. But Hubble's observation in 1929 changed everything. The galaxies were not fixed points in a static void. They were carried by the flow of expanding space itself, like leaves drifting apart on an inflating sea. Einstein, upon learning this, would later call his cosmological constant the greatest blunder of his career. The universe had a history. If it was expanding today, then in the past it must have been smaller, denser, hotter. Suddenly, the idea of a cosmic beginning, once dismissed as theological speculation, emerged as a scientific reality. Georges Lemaître, a Belgian priest and physicist, had already proposed such a notion. The primeval atom, a fiery origin from which all of space and time had unfolded. His theory, once ridiculed, now seemed inevitable. Yet, as monumental as this discovery was, it carried with it a silent assumption. Gravity, the great architect of the cosmos, should act as a brake. Over time, as galaxies pulled on one another, the expansion should slow. Whether the universe would one day halt and collapse back into itself, or continue forever, but at a dwindling pace, depended on the total amount of matter and energy it contained. For decades, astronomers searched for the answer. They measured the density of galaxies, the distribution of dark matter, the hidden mass in galaxy clusters. All of it fed into the great question: would gravity's hand eventually stop the expansion? By the mid-20th century, most scientists were convinced that cosmic deceleration was inevitable. The only debate was how much matter was out there, and whether the universe's story would end in Phyra, Big Crunch, or in a slow eternal fade. The stage seemed set, the narrative clear. Expansion, born from the Big Bang, would gradually be tamed by gravity's embrace. The cosmos was vast, mysterious, but predictable. And then came the 1990s. Astronomers turned to one of the most reliable cosmic yardsticks, Type Ia supernova. These stellar explosions occur when a white dwarf star, locked in a binary system, siphons matter from its companion until it reaches a critical mass. At that moment, carbon ignites in a runaway fusion reaction, tearing the star apart in a titanic blast. The brilliance unleashed is so uniform, so consistent, that Type Ia supernova serve as cosmic standard candles by measuring their brightness. Astronomers can determine their distance across billions of light years. Two teams set out to use these explosions as cosmic beacons. The Supernova Cosmology Project, led by Saul Perlmutter in California, and the Heisey Supernova Search Team, led by Brian Schmidt and Adam Rees, worked independently but with the same goal: to map the expansion history of the universe. If the cosmos was slowing under gravity's pull, distant supernova should appear slightly brighter than expected. Their light would have traveled through a universe that had been expanding faster in the past, but gradually easing its pace. The data would reveal how quickly the cosmic engine was winding down. The observations began to arrive, night after night. Telescopes captured the fading glow of ancient detonations, their light stretched and reddened by billions of years of expansion. The teams carefully measured their luminosity, compared them against models, and calculated the distances. What they found was not just surprising, it was unsettling. The supernova were dimmer than expected. too dim, they were farther away than they should have been if the universe's expansion was slowing. Instead of decelerating, the expansion appeared to be speeding up. The cosmos was not coasting toward rest, it was accelerating. This result defied reason. Gravity, the one force capable of shaping the fate of the universe, could only slow expansion, never accelerate it. To explain what the data revealed, scientists were forced to resurrect an idea once abandoned, a mysterious energy permeating space itself, pushing the fabric of the universe apart. Dark energy, a name given to an unknown cause, a placeholder for a force unlike any other in physics, invisible and yet stronger than gravity on cosmic scales. Its presence meant that the majority of the universe was not made of matter at all, but of something utterly strange, something that defied detection except through its effect on the expansion of space. The revelation struck the scientific world like a thunderclap. Decades of expectation had collapsed in an instant. Instead of a universe destined to slow, it was one racing ever faster into the future, its galaxies accelerating into an unreachable horizon. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics for this discovery. Their work did not just add a new chapter to cosmology, it rewrote the foundation of the field. The universe was not just expanding, it was accelerating into an unknown future. And with that realization, a deeper mystery emerged. What is this dark energy? Where does it come from? Is it constant, or does it evolve with time? Will it drive the cosmos into eternal expansion, tearing galaxies apart in the distant future? Or will it change its nature and alter destiny once again? The answers remain hidden, waiting in the silence between galaxies. But one truth is certain. What began with Hubble's quiet measurements on glass plates in the 1920s has grown into one of the greatest enigmas in science. The cosmos is not only larger and older than once believed, it is stranger than human imagination ever dared to conceive. And the discovery of its accelerating expansion marked the moment when humanity realized it was adrift in a universe whose fate remains unknown. Chapter 2: Scientific Shock. When the verdict arrived, it struck like a blow against the very logic of nature. The universe, instead of slowing under the weight of its own gravity, was accelerating. A cosmos that should have been tethered by attraction was, instead, propelled outward by some unseen hand. For a century, physics had lived in the shadow of Einstein's equations. General relativity was not only a triumph of mathematics, it was a philosophy of how space, time, and matter dance together. Its predictions had guided astronomers to black holes, to gravitational waves, to the bending of starlight itself. And within that framework, one principle seemed absolute: gravity attracts. No matter the scale, whether the fall of an apple or the orbit of galaxies, the pull was always inward. Expansion, if it existed, should always be slowing. The discovery of acceleration was more than an unexpected measurement. It was an affront to the order of physics itself. To understand the shock, one must return to the earliest days of relativity. In 1917, Albert Einstein attempted to apply his new equations to the entire universe. The mathematics insisted that space must be in motion, either expanding or contracting. But like many of his contemporaries, Einstein assumed the cosmos was static. To force balance, he introduced a new term, the cosmological constant. This symbol, lambda, acted as a kind of repulsive gravity, countering attraction and holding the universe steady. It was a delicate contrivance, a patch stitched onto the seamless fabric of relativity. When Hubble's discovery of expansion arrived a decade later, Einstein abandoned it. "The greatest blunder of my life," he is said to have remarked, regretting the unnecessary complication. For decades afterward, lambda was relegated to a footnote in textbooks, a historical curiosity. And then, almost a century later, the supernova spoke. Their fading light carried a message across billions of years. The universe was not slowing, but racing ahead. The abandoned constant was suddenly reborn. No longer a blunder, but the only known way to reconcile theory with observation. The idea was staggering. Space itself contained an energy, invisible and immeasurable by any known detector, yet strong enough to overcome the gravity of galaxies. This energy did not dilute as the universe expanded, remained constant, woven into the fabric of spacetime. As the cosmos grew, more space appeared, and with it, more of this strange energy, accelerating expansion ever further. Scientists called it dark energy. The name was not an explanation, but an admission of ignorance. It was not matter, for matter clusters into galaxies and stars. It was not radiation, for radiation thins as the universe stretches. It was not any known field of physics. It was simply something, an unknown pressure suffusing all of reality. By the late 1990s, the measurements were clear. At least 68% of the universe's energy budget belonged to this hidden entity. Ordinary matter, the stars, the planets, the elements of life made up less than 5%. Dark matter, unseen but gravitationally binding galaxies, claimed about 27%. But dark energy dominated all. The balance of reality had shifted. The familiar universe of atoms and light was only a thin surface. Beneath it, a deeper ocean lay in shadow. For physicists, the shock was not only in the numbers, but in the silence that followed. No established law, no tested principle offered an answer. Quantum field theory predicted that empty space should indeed have energy, but its estimates overshot reality by a factor of 10. 120, a discrepancy so vast it became known as the worst prediction in the history of science. Supersymmetry, string theory, hidden dimensions, none provided a satisfying explanation. The scientific community stood at a precipice. For centuries, progress had meant peeling away mysteries, replacing wonder with equations. But here was a phenomenon that defied all expectation. Dark energy was not a detail to be resolved. It was a wall, an abyss at the edge of physics. The philosophical implications were profound. If the cosmos was accelerating, its future was no longer one of gentle, slowing, or graceful collapse. Instead, galaxies would drift farther apart, their light stretched beyond visibility. Stars would burn out, and the universe would become darker, colder, lonelier. An eternity of expansion awaited, an infinite silence. Some speculated even more dramatic ends. If dark energy were to grow stronger with time, it could tear apart galaxies, then stars, then atoms themselves, a big rip where the fabric of reality is unraveled. Others imagined a universe in which dark energy decayed, returning power to gravity and perhaps triggering a new cycle of collapse and rebirth. But the present offered no such clarity, only a single unsettling truth. Most of the universe is made of something unknown, something no laboratory can isolate, something no telescope can see. In scientific circles, this was more than a discovery. It was a humiliation. The triumphs of the 20th century relativity, quantum mechanics, the standard model of particle physics, had given the illusion of nearing completion, as if the great puzzle of the cosmos was nearly solved. Dark energy shattered that illusion. It reminded humanity that beneath the surface of understanding lies an ocean of ignorance. The shock was not only intellectual, it was emotional. For the first time, cosmology was no longer about what the universe contained, but about what it concealed. The night sky, once a map of stars and galaxies, became a mask hiding an invisible force. The familiar became unfamiliar. The solid ground of science gave way to uncertainty, and in that uncertainty lay both terror and wonder. Because to admit ignorance is also to admit possibility. Dark energy could be the key to new physics, a bridge beyond the known, a window into the foundations of reality itself. It could reshape not only cosmology, but the very laws that govern existence. The scientific shock was not merely the discovery of acceleration. It was the realization that the universe was stranger than anyone had dared to imagine, and that the greatest mysteries still lie ahead. The story of science had entered a new chapter, one written not in answers, but in questions, and at its heart stood a single enigma: the invisible pressure filling the cosmos, propelling galaxies apart and forcing physics itself into silence. Chapter 3: Deeper Investigation. The first shock of discovery never lingers alone. In science, each revelation becomes a summons to test, to measure, to confirm. And so it was with the accelerating universe. The dim light of distant supernova had whispered a truth that defied gravity itself. But whispers, however convincing, demanded an echo. To probe the cosmos, astronomers turned to its oldest light, the afterglow of creation itself. In 1965, Arno Penzias and Robert Wilson stumbled upon the faint hiss of microwave radiation, a uniform glow saturating the sky. It was the fossil of the Big Bang, the cosmic microwave background. Born when the universe was only 380,000 years old, this light carried the imprint of the first atoms, the seeds of all future galaxies. Its discovery won a Nobel Prize, but its significance stretched far beyond recognition. Here was a cosmic ledger recording the earliest chapters of the universe's expansion. Decades later, NASA's COBE satellite sharpened the picture. In 1992, it revealed the CMB's subtle irregularities, tiny fluctuations in temperature, no larger than 1 part in 100,000. These ripples were the fingerprints of quantum fluctuations magnified by cosmic inflation, destined to grow into galaxies and clusters. Then came WMAP, launched in 2001. It extended COBE's work, mapping the microwave sky with exquisite precision. Its data confirmed the geometry of space itself, flat, not curved, as predicted by inflation. More importantly, it reinforced the shocking conclusion. To explain the observed patterns, the universe required not just dark matter, but dark energy, making up roughly 2/3 of the cosmic balance. The supernova measurements were not an anomaly, they were a cornerstone. Finally, in 2009, the Planck satellite delivered the most detailed portrait yet. For 4 years, it measured the microwave background with unprecedented accuracy, charting the infant universe in stunning detail. Its results refined the cosmic recipe: 68% dark energy, 27% dark matter, 5% ordinary matter, numbers carved into the very structure of spacery. Yet these maps also revealed something else: an uneasy tension. The rate of expansion deduced from the early universe, frozen into the CMB, was not the same as the rate measured in the nearby cosmos through supernova and Cepheid stars. Two rulers of time, two answers, both precise, both irreconcilable. The cosmos was speaking in contradictions. This discord came to be known as the Hubble tension. Planck's measurements suggested a slower expansion, about 67 kilometers per second per megaparsec. Local observations, however, insisted on something faster, around 73. The gap was small but persistent, far beyond the reach of statistical error. Either hidden systematics haunted the data, or the laws of physics themselves changed between the early universe and today. The tension grew sharper as more measurements arrived. The Hubble Space Telescope, using Cepheid variables as distance markers, confirmed the higher value. Ground-based surveys of galaxies echoed the same. The contradiction could not be dismissed. Something fundamental was missing from the picture. Meanwhile, another tool began to weave the cosmic story: the great surveys of galaxies across billions of light-years. Telescopes mapped the distribution of matter on the grandest scales, revealing a universe not uniform but sculpted into a vast cosmic web. Filaments of galaxies stretched like strands of glass, threading across the night, separated by immense voids. These structures bore silent testimony to expansion. The voids, vast and empty, swelled as the universe aged, their boundaries etched by walls of galaxies receding ever farther apart. The filaments, delicate yet immense, stretched across space, shaped not only by gravity, but by the unseen influence of dark energy. Expansion was not smooth. It breathed through the cosmos, carving structure, shaping the very geometry of existence. Instruments refined the measurements: baryon acoustic oscillations, sound waves frozen in the distribution of galaxies offered a new cosmic yardstick. Their patterns confirmed the story told by supernova and the CMB alike. Dark energy was real, its grip woven into the expansion across time. Yet, anomalies persisted. Some regions of the CMB seemed colder than theory allowed. Vast patches, like the so-called cold spot, hinting at statistical flukes, or perhaps new physics. Other surveys revealed galaxies forming faster than expected, stars blazing brighter than models predicted. The discord was subtle but persistent, as if the universe were offering clues in riddles. The deeper the investigation, the stranger the picture became. The Hubble tension sharpened into a possible fracture in cosmology's foundation. Was dark energy truly constant, a cosmological constant as Einstein once imagined? Or was it evolving, changing over time, its strength waxing or waning like a hidden tide? Could new particles, new forces, even hidden dimensions account for the discrepancy? Or was it a message from the earliest moments of the Big Bang, a signal that inflation itself had left behind more than ripples, perhaps a scar? no answer has yet emerged. But the precision of instruments grows ever finer. The Hubble Space Telescope refined the distance ladder with unmatched clarity. Ground-based observatories Kaksubaru, the Very Large Telescope, extended the reach. Soon, the James Webb Space Telescope would pierce even deeper into the past, measuring faint galaxies from the first billion years. Each new observation added weight, sharpening the paradox instead of dissolving it. The result is a cosmos both mapped and mysterious. On one hand, its broad strokes are clear, a universe born hot and dense, expanding and cooling, structured by dark matter, driven by dark energy. On the other, its details slip through understanding, leaving gaps no theory can yet fill. For science, this duality is both triumph and torment. To measure the universe so precisely, to chart its expansion across billions of years, is a feat unparalleled. And yet, to hold data that refuses reconciliation is a reminder that the cosmos is not obliged to be simple. The deeper the investigation, the clearer the outline of ignorance becomes. The accelerating universe is not only relit, is tangled with tensions and contradictions that hint at deeper layers of truth. Somewhere beyond the precision of Planck, beyond the flicker of supernova, beyond the web of galaxies, lies the missing key, and so the mystery deepens. The universe, instead of yielding to observation, resists. It offers glimpses of clarity, only to cloak itself again in paradox. Each map, each survey, each telescope sharpens the picture, but also sharpens the unknown. The investigation does not end with data, it begins there. For in the patterns of light and void, in the whispers of ancient photons, in the discord of expansion rates, the cosmos is telling a story, still unfinished, a story that suggests physics itself may not yet be complete. Chapter 4: Escalation. Mystery deepens. The expanding universe is not a quiet drift into the unknown. It is a relentless acceleration, a cosmic surge that stretches the fabric of reality faster with each passing moment. For astronomers, the revelation was more than a curiosity of data. It was a sentence written across time. The universe is not bound toward reunion, but toward separation. Galaxies, once gravitational companions, are being carried apart by a tide no star can resist. The consequence is profound. In billions of years, galaxies beyond the local group will fade beyond the reach of light. Their glow, stretched and redshifted, will slip past visibility until only silence remains. The night sky, once crowded with clusters and filaments, will empty. To future observers, the universe will appear smaller, lonelier, stripped of its cosmic truth. This vision has been named the Big Freeze. The Big Freeze is a universe without fire. Stars consume their fuel, their fusion dwindling, until only cinders remain. Red dwarfs, burning faintly for trillions of years, will one day exhaust their last reserves. White dwarfs will fade into black, neutron stars into cold monuments of collapsed matter. Even black holes, the final captives of gravity, will evaporate through Hawking radiation, dissolving into nothing. Expansion ensures that no new structures will form. No galaxies will collide to ignite fresh generations of stars. The cosmos will grow dim and then dark, and then silent in eternal frost. But there is a fate more violent and more terrifying. If dark energy is not constant, if it strengthens over time, Its grip on the universe could tighten into catastrophe. Expansion would not simply carry galaxies apart, it would accelerate without bound. First, the great walls of clusters would be pulled apart. Then galaxies themselves would be torn from within, their stars scattered like sparks in a storm. Stars would be ripped from orbit, planets from their suns, moons from their planets. And if acceleration continued unchecked, the tearing would plunge deeper still. The fabric of matter itself, molecules, atoms, even protons, could be ripped apart by the runaway stretching of space. This is the Big Rip, a universe annihilated not by fire, not by ice, but by expansion itself. The mathematics of such a fate are chilling. Depending on the properties of dark energy, whether its density remains constant or increases, this cosmic disintegration could occur tens of billions of years from now, or sooner. The end would arrive everywhere at once, with no refuge, no sanctuary. Expansion itself would dismantle the foundations of physics. This possibility unsettles not only imagination, but the laws of science. For what does it mean if the very constants of nature are not constant? If the scaffolding of reality can collapse under its own equations? Dark energy does not merely shape the future. It threatens to unravel the principles upon which physics rests. Cosmology has long been descriptive, a science of origins and structures, tracing galaxies and stars across time. But with the discovery of acceleration, it has become existential. The fate of the universe is not an abstract curiosity. It is a truth with consequences, a horizon that defines meaning itself for humanity. These timescales stretch far beyond comprehension. Civilizations rise and fall in the blink of cosmic time. Stars live and die while galaxies orbit in silence. Yet the knowledge that existence itself is fragile, that space can not only expand but dismember its own creation, casts a long shadow, and still the universe keeps its secret. No measurement yet reveals whether dark energy is constant or evolving, whether it will guide the cosmos into an endless freeze or a violent rip. The data whisper possibilities, but none offer certainty. The mystery deepens, not just in what the universe will become, but in what it truly is. Expansion is no longer merely a story of galaxies drifting apart. It is a revelation that physics itself may not be permanent, that the universe may be built on laws destined to change, to dissolve, to vanish. This is the new frontier, not the stars, not the galaxies, but the question of whether existence itself can endure. And so, under the quiet light of distant supernova, the deepest truth emerges. The accelerating universe is not only a challenge to science, it is a challenge to meaning. The cosmos is not only expanding, it may be unraveling. Chapter 5: Theories and Speculations. The mystery of the accelerating universe is not only an observational riddle, it is a challenge thrown at the foundations of physics, demanding explanations where none seem to fit. From the first moment, astronomers realized the cosmos was speeding apart. Theory raced to catch up. What could drive space itself to accelerate? What hidden engine could overpower gravity on the grandest scales? The first suspect was not new. It was a ghost from the past, Einstein's cosmological constant. In 1917, Einstein had introduced the constant lambda as a balancing force, a repulsion built into space itself. When Hubble revealed expansion, Einstein abandoned it. Universe seemed to resurrect lambda from obscurity. Perhaps, scientists reasoned, it was not a mistake after all. Perhaps the vacuum of space is not truly empty, but infused with a subtle energy, uniform and unchanging, pushing galaxies apart. In this picture, every cubic centimeter of space carries a minute amount of energy. As the universe expands, more space appears, and with it, more energy, keeping acceleration constant. This simple idea matched the data, but it carried a haunting problem. Quantum field theory, the framework of modern physics, also predicts vacuum energy. Every field, every particle, contributes a baseline of energy to the vacuum, even in its lowest state. But when physicists calculate the total, the result is catastrophic. The predicted energy is 10 times larger than what the universe displays. No discrepancy in science is greater. This is not merely error, it is absurdity. A mismatch so vast it suggests something is deeply broken in our understanding of reality. If the cosmological constant is correct, then quantum theory is incomplete in ways not yet imagined. If quantum theory is correct, then the constant cannot be what it seems. Faced with this paradox, some turned to new ideas fields, unlike any seen before, shifting with time, subtle as whispers. These became known as scalar fields, or more evocatively, quintessence. Quintessence imagines dark energy not as a fixed constant, but as a dynamic entity, an evolving energy field stretching across the universe. Unlike the cosmological constant, which remains steady, quintessence could grow weaker or stronger, shaping the fate of the cosmos in ways far less predictable. If its strength diminishes, acceleration may one day slow, perhaps even reverse. If it grows, the Big Rip may await. Yet no evidence of quintessence has been found. No particle collider, no detector has glimpsed such a field. For now, it remains a mathematical possibility, a ghostly speculation drifting beyond reach. Others took a more radical path. Perhaps dark energy is not a thing at all. Perhaps it is a sign that the very law of gravity is incomplete. General relativity has passed every test within the solar system, from the bending of light around the sun to the ripples of spacetime, measured as gravitational waves. But on cosmic scales, billions of light years, it has never been directly tested. Could the acceleration be evidence that Einstein's masterpiece is only an approximation? Theories of modified gravity attempt to answer this. Some suggest extra dimensions, where unseen geometries influence cosmic motion. Others propose subtle corrections to relativity, changes invisible locally but profound across the universe. Yet each attempt must not only explain acceleration, but also preserve all that relativity has already explained with perfection. So far, no alternative has succeeded without contradictions, and still more daring speculations rise. Some theorists look to the multiverse, an idea born from inflation, the rapid expansion that ignited the Big Bang. In many models, inflation does not end everywhere at once. Instead, it continues eternally, spawning countless bubble universes, each with its own laws and constants. If this is true, then dark energy in our cosmos may be a product of cosmic chance. Perhaps countless universes exist, each with different vacuum energies. In most, the values are too high or too low for galaxies, stars, or life to form. Only in rare universes like ours does acceleration take the delicate form that permits existence. It is a staggering thought that dark energy is not explained, but selected. That we live in a universe not because it is natural, but because it is habitable. But speculation can grow darker still. In the equations of particle physics, the vacuum of our universe may not be the lowest possible state. It may be a false vacuum, a metastable plateau in the landscape of energy. If this is true, then dark energy could be the faint echo of instability. Some data tomorrow, or billions of years, hence a quantum fluctuation, could trigger a collapse, a bubble of true vacuum, expanding at the speed of light, rewriting the laws of physics as it spreads. Within its wake, atoms, chemistry, even the structure of matter would dissolve. The universe would not simply end, it would transform into something alien, indifferent, and unrecognizable. This possibility is called vacuum decay. And though it is only a hypothesis, it lingers as one of the most unsettling visions ever imagined by science. Each of these ideas, cosmological constant, quintessence, modified gravity, the multiverse, vacuum decoffers a path toward explanation. Yet none close the mystery. Each raises as many questions as it answers. Why does the cosmological constant take its tiny value? What field could embody quintessence? How can gravity be altered without breaking relativity's proven triumphs? If the multiverse exists, how could it ever be tested? If the vacuum is unstable, what determines when and where the end will come? Science thrives on clarity, on equations that not only describe but predict. Dark energy refuses such resolution. It stands as a mirror, reflecting ignorance rather than knowledge, possibility rather than certainty. For now, the accelerating universe remains an open wound in physics, a reminder that even the most elegant theories can fail before the vastness of reality, a signal that beneath the surface of the known lies a structure stranger, deeper and more elusive than imagination has yet conceived. And so the speculation continues, not as idle curiosity, but as necessity. To confront dark energy is to confront the limits of human thought. Each theory is not an end, but a door, opening into corridors of deeper questions. What is dark energy? A constant, a field, a flaw in gravity, a quirk of the multiverse, a symptom of a doomed vacuum. The only certainty is uncertainty. The accelerating universe demands answers, but for now, it offers only mystery. Chapter 6: Scientific Tools and Ongoing Testing. The mystery of dark energy is not only written in equations and theory, it is also etched into the skies, waiting to be revealed through instruments of extraordinary precision. To measure the invisible, humanity builds mirrors to the cosmos, machines of glass and metal that transform faint light into knowledge. Each telescope, each survey is a probe into the hidden fabric of reality. The quest began with wide eyes cast across the heavens. The Sloan Digital Sky Survey, launched at the turn of the millennium, charted galaxies across the night like stars upon a map. Its sweeping gaze revealed filaments stretching for billions of light years, vast structures where matter gathered and voids where it fled. In these patterns lay a story, expansion not as a smooth swell, but as a sculptor shaping a cosmic web. The SDSS did not merely count galaxies. It traced the bones of the universe itself. From this work, the Dark Energy Survey was born. Operating from the Chilean Andes, its 570-megapixel camera recorded the light of 300 million galaxies. It reached back 7 billion years, a time when acceleration was only beginning to dominate. By measuring the bending of light through gravitational lensing and the clustering of galaxies, Day tested expansion with precision greater than ever before. Its findings strengthened the case. Dark energy was real, and its hand upon the universe was undeniable. Yet every confirmation bred deeper unease. The data agreed with the broad strokes of acceleration, but faint tensions, small misalignments, hinted that something remained concealed. To sharpen the image, new instruments were needed. Europe's Euclid telescope, launched in 2023, was crafted. For this purpose, with a 1.2-meter mirror and a wide field of vision, Euclid set out to chart 2 billion galaxies across a third of the sky. Its mission: to map the geometry of the universe, to measure how structures grew under gravity, and to see how dark energy influenced their fate. Euclid's design allowed it to peer across 10 billion years of cosmic history, bridging the gap between the young universe and the present. If successful, its data could reveal whether acceleration has remained constant, as a cosmological constant would suggest, or shifted over time, as quintessence might demand. But not all eyes were fixed upon dark energy directly. Some sought to understand it by reaching farther into the past, to witness the dawn of galaxies themselves. The James Webb Space Telescope, stationed at the L2 point beyond the Earth and Moon, unfolded in 2021 as a cathedral of infrared vision. Its golden mirrors captured light stretched by billions of years of expansion. By studying the earliest galaxies, those born only a few 100 million years after the Big Bang, Webb offered a way to test cosmology across epochs. If galaxies appeared earlier, brighter, or larger than models predict, it could signal that the underlying assumptions about expansion must change. Already, Webb has raised questions. Some of its first images revealed galaxies unexpectedly massive at astonishingly early times. While not yet a definitive challenge, such findings whisper of tensions, as though the story of growth may not align perfectly with expectations. Whether this reflects astrophysical processes or deeper cosmological revisions remains an open debate, and still new tools are being prepared. The Nancy Grace Roman Space Telescope, planned for launch in the coming decade, is designed with dark energy as its central target. With a field of view 200 times greater than Hubble's, it will capture sweeping panoramas of galaxies and supernova. Roman's mission is to measure the expansion rate directly, to confront the Hubble tension with clarity sharper than ever before. Beyond light, a new messenger has entered the stage: gravitational waves. First detected in 2015, these ripples in spacetime allow astronomers to measure distances in a way independent of traditional methods. A neutron-star collision, observed in 2017, provided the first demonstration. Such events could serve as standard sirens, cosmic lighthouses, announcing their distance through gravity itself. If enough are recorded, they may offer a new ladder of expansion, free from the uncertainties of light-based techniques. The era of gravitational wave astronomy is still young, but its promise is vast. with detectors growing more sensitive, the next decades may see the universe's expansion tested by the tremors of space-time itself. The search does not end with telescopes. Beneath mountains and within accelerators, physicists pursue dark energy's shadow in other forms. At CERN and laboratories worldwide, particle collisions probe for hidden fields or exotic forces that could mimic dark energy's effect. Experiments test whether fundamental constants drift with time, or whether unseen particles influence cosmic evolution. The work is meticulous, indirect, but essential. If dark energy arises from a field, its fingerprints may linger in the quantum world, across continents and disciplines. The effort is unified. Astronomers, physicists, engineers, and theorists all converge upon the same enigma. The tools differ: optics, electronics, mathematics, but the aim is singular: to understand the invisible force that reshapes the universe. Yet even as instruments sharpen, mystery deepens. Each new survey confirms acceleration, but the cracks between measurements widen. The cosmic microwave background paints one story, local galaxies tell another. The Hubble tension endures, unresolved, growing sharper with each attempt at precision. Science advances by closing gaps, but dark energy seems to widen them. As though the closer it is studied, the more it slips from grasp. The unity of the scientific community around this pursuit speaks to the magnitude of the challenge. This is not a puzzle of detail, but of foundation. To explain dark energy may require a new physics, a reimagining of space, time, and vacuum. For now, humanity builds its machines, gathers its data, and waits for the universe to speak. Each photon captured by Euclid, each ripple measured by LIGO, each image from Webb is a piece of a larger mosaic. Slowly, patiently, the pattern forms. Whether it reveals the nature of dark energy or points to mysteries deeper still remains unknown. But the search is relentless, carried forward by the collective resolve of a species unwilling to accept ignorance as the final word. The cosmos accelerates into the future, but science pursues with equal determination. The race is not to stop expansion, but to understand it, and in that pursuit, humanity glimpses its own reflection, a civilization fragile and finite, yet capable of building instruments that measure the drift of galaxies, the tremor of spacetime, the whisper of the void. The mystery is vast, but so too is the will to confront it. Chapter 7: Philosophical Reflection, Emotional Close. The expansion of the universe is not only a story of galaxies and equations, it is also a story of longing. In every widening of the cosmos lies a reminder of the widening distance between humanity and what it seeks to hold. The revelation that the universe is accelerating is, in part, a scientific fact, but it is also an existential message. Each distant star drifts farther, each galaxy recedes faster, as though creation itself were pulling away from comprehension. For every measurement gained, the horizon of mystery grows larger still. The universe speaks, but always in whispers, just beyond the range of certainty. To many, this silence feels deliberate. It is as though the fabric of reality has been woven with threads of concealment, designed not to yield fully to inquiry. Every new discovery answers one question, only to unmask a dozen more. Knowledge grows, yet the unknown expands faster. This pattern mirrors the very cosmos it describes. Expansion is not only written into galaxies, but into the pursuit of understanding itself. Human beings press outward, building instruments to pierce the veil, only to find the veil has stretched farther still. And so the accelerating universe becomes a metaphor for the accelerating mystery of existence. What if some truths are not merely undiscoverable, but undiscoverable? What if the very structure of space and time ensures that certain answers remain forever hidden, sealed beyond the event horizon of comprehension? This possibility does not silence inquiry, it deepens it. There is dignity in the attempt, even if the summit of truth cannot be reached. In the striving itself lies a reflection of humanity's essence, fragile, finite, yet unwilling to abandon the chase. Albert Einstein once confessed, "The most incomprehensible thing about the universe is that it is comprehensible." It was an acknowledgement not of certainty, but of astonishment that minds so brief, so limited, could grasp even fragments of the cosmic order. Yet the incomprehensible remains vast, dwarfing the islands of clarity. Perhaps comprehension itself is a miracle, a brief window in an otherwise opaque expanse. The accelerating cosmos reminds humanity of its place, not as masters of the universe, but as participants within it. Drifting on a small planet around a modest star, pressed by a force unseen, humanity confronts the vast indifference of space. And yet, within that indifference, it discovers meaning of its own making. For the silent expansion is not a void, it is a stage. Every galaxy that drifts away also testifies to the fleeting moment in which it could be seen at all. Every receding horizon underscores the preciousness of the present view. The stars are not eternal companions, but passing voices in a cosmic song. In this perspective, fragility becomes a form of beauty. The knowledge that galaxies will one day vanish beyond reach does not diminish them. It makes their light more profound. To witness them now is to share a moment that will never return. Science captures not only data, but the fleeting grace of existence itself. The universe accelerates into an unknowable future. Its fate may be cold emptiness, or disintegration, or something yet beyond imagination. But whatever the end, the present is luminous with wonder. Humanity sails upon this expansion, carried into the dark, without a map, yet with eyes that look upward. In every observation lies a quiet defiance, a refusal to let the silence of the cosmos erase the voice of curiosity. The story of dark energy is unfinished. It may never be finished. And perhaps that is its deepest lesson, that existence is not a problem to be solved, but a mystery to be lived. The galaxies continue their retreat. The cosmic web stretches, filaments thinning, voids widening, and through it all, a fragile species measures, questions, reflects. The silent expansion is more than physics. It is a mirror of human fragility and of human greatness, a reminder that even in the face of the infinite, meaning can be drawn, beauty can be seen, and wonder can endure. The cosmos unfolds without end, an eternal horizon, carrying its travelers outward into an ocean without shore. And within that silent tide, the human story drifts forward, finite, yet luminous, written in the starlight of a universe forever beyond reach.